sample structures.
Okay, thank you. So I'm going to keep it very simple. I will give essentially 3 problems for the classical theory of probability, 3 questions that I believe cannot formally be resolved without moving away from the idea that a sample space for a probability is a set. That's it. So let me remind you of the classical picture. So the classical picture, I should also say everything that's in the everything I'm going to say is in the handout. So it's going to be short. The handout is long because there's nothing more that in it that I'm going to say. I just decided to put everything in there to refer back to it. So the classical picture of the formalization of probability goes roughly as follows. You have a set, which is called the sample space. Its elements, little omega, are called outcomes. A subset of this set is an event. And assuming that omega is finite, which I'm going to assume throughout, I'm going to take the simplest possible case, we can take a probability to be simply a function from omega to 0, 1, such that p omega such that, well, okay, I suppose it has to be on subsets. Let's define it on subsets of omega such that the probability of the subset consisting of 2 outcomes is equal to the sum of their probabilities. And such that the whole set is given value 1. That's it. Okay, extremely simple. Extremely simple. That's all I'll need. There's less stuff than really should be in there, but that's all I'll need. At least this stuff should be in there. Okay. What is the main thing that this formalization depends on is this idea that when we talk about outcomes, really all we care about is whether something has happened or hasn't happened. So the reason why we tend to formalize this as a set is because whenever we have 2 outcomes in an experiment, say, we want to be, say, definitively be able to say whether they're the same outcome or whether they're not the same outcome. And a set formalizes that very well. 2 elements of a set are either equal or not equal. That's it. And from that it follows that an event, which is just a set of outcomes, is either equal or unequal to another event. So these are subsets of omega. I should say omega. Okay, so for example, the simplest example, the classic example, the sample space for a coin flip would be something that can be written like this, heads and tails. Heads is an outcome that is distinct from tails, which is also an outcome. And this means that the event, the coin landing heads, is not the same thing as the event, the coin landing tails. Okay, and essentially the whole theory of probability is built, the whole formalization of the theory of probability is built on these features of sample spaces. They are comprised of maximally distinguishable points, and that's it. Okay. When does this thing become problematic? So I'm going to raise 3 issues. So what I want to claim, so let me preface where I'm going to be heading with this. What I want to claim is that there are situations, there are questions you can ask about probability that intuitively make sense, whose formalization in terms of a sample space that is a set leads inevitably to confusion. Okay, so there's 3 problems I'm going to raise, and I'm going to solve them by moving away from this picture. So this is going to become a structure, and I'm going to say what the structure is later. Okay, so what are the 3 problems? Okay. So I'm going to maybe put them in the form of a question. Question 1. Let S be a 4-element set. Set, i.e. the cardinality of S is 4. So, question, what is, let S be a 4-element set with a group structure. If you don't know what a group is, it doesn't matter. With a group structure. What is the probability? The probability that with a group structure G, say, that G is the so-called Klein group. So what the Klein group is and what groups are in general doesn't really matter. What matters is that it's a basic mathematical fact that there's up to isomorphism, there's 2 group structures, 2 distinct group structures on a set of 4 elements. Okay. I claim there's no reasonable way to answer this in the classical setting. I mean, the thing you can do, you can try and, so when you're given a 4-element set, you know that as a group, it'll be either the so-called cyclic group on 4 elements or the Klein group. Again, doesn't matter what these things are. So of course, you can take your sample space to consist of 2 points, and then if you're choosing uniformly between them, you can say that the probability of choosing the Klein group is a half. Fine, you can do that. You shouldn't, though. All right. The second problem.
Wait, did you say why that was the problem?
No, it's a question, an open-ended question. It's a question that somehow, yeah, okay, but I'm not calling it just really a problem. It's how do you approach this question, the classical theory of probability? You need to come up with a set as a sample space that somehow involves the possibilities, which in this case are 2. So you can probably come up with arguments about why this shouldn't be a half or shouldn't, but it seems to me there's no principled way to do this. Insofar as you say there's 2 distinct isomorphic structures in a 4-element set, the probability is either going to be it's either going to be the Klein group or the cyclic group on 4 elements. The formalization doesn't really allow you to do anything else. Okay, now this is maybe an actual problem. So this is called the Sleeping Beauty problem. It's kind of a famous problem in philosophy of something or other. I'm not sure exactly where it belongs. Philosophy of epistemology, maybe. I don't know. Physicists also like it. All right. So the Sleeping Beauty problem roughly says the following. There's someone that's called Sleeping Beauty, because that's what she was called in the original paper, and there's an experiment that's being run, and the experimenters are going to flip a coin. If it lands tails, if it lands heads, they're going to wake up, they're going to put Sleeping Beauty, they're going to put Sleeping Beauty to sleep and wake her up on Tuesday. If it lands heads, if it lands tails, they're going to put her to sleep, wake her up on Monday. Let's assume it's Sunday when this is being described. They're going to wake her up on Monday. They're going to ask her, what is your, okay. They're going to wake her up on Monday. Then they're going to put her back to sleep. They're going to give her a pill that makes her forget everything. They're going to put her back to sleep and then wake her up again on Tuesday. Every time she wakes up, whether it's heads or tails, they're asking her, what do you think the chances are that the coin we flipped that determined the sleeping pattern landed heads or landed tails, say? Okay. So I should probably ask, does anyone have any intuition about this, what the answer to this should be?
Yeah.
Should be a half, okay. What about the Sleeping Beauty, those that know about it? Okay, so the...
Elkis is a third, I want to say.
So let me tell you, let me describe in terms of a sample space what the perplexion is supposed to be. There's three events that take place. Either the coin lands heads and Sleeping Beauty gets woken up on Monday, or the coin lands tails and Sleeping Beauty gets woken up on Monday, or the coin lands tails and Sleeping Beauty gets woken up on Tuesday, say TT. Okay? Now, since Sleeping Beauty has woken up, so the argument goes, even though she knows that the coin is objective, it's fair, it's been flipped, still, she will be awake in 2 out of 3 situations when she'll be woken up. It'll be when the coin has landed tails. So, the argument goes, she should say 2/3. The probability that the coin landed tails is 2/3. And if you formalize the Sleeping Beauty problem in this way, with this as your sample space, with a set of distinguishable things, and kind of ignoring the pill that makes these two things indistinguishable, sure, it's fine. 1/3 is a perfectly sensible thing you can argue about. Okay, that's the second perplexion. Now the third one, let me write it here. The third one is the three-sided die. Okay. So there's a three-sided die. Does such a thing exist? Well, it does, apparently. You can actually construct it. It's interesting that people don't have a physical intuition about it. I think it's important for this example because people tend to think about fair three-sided die. People tend to think, what is a fair three-sided die? Well, it's something that with a probability 1/3 lands on each side. But there is actually a physical object, apparently. I didn't know about this. Before I came up with this, before I knew whether there can be a physical manifestation of a three-sided die, but there can be, apparently. Okay, so you have a three-sided die, and you have, which I'm going to represent this way, and you have 1 written on one of its sides and two written on the other 2 sides. So the question is, what is the probability that in one roll of the die you get 2? You get the number 2. Intuitions? Fair three-sided die.
2/3.
2/3, right? How would you formalize this? So the first naive thought is you do this. But that as a set, of course, is equal to this. So then the 2/3 answer doesn't quite work. unless, of course, you stipulate that this is 2/3. But let's assume everything's going to be uniform today. I'm going to make no arbitrary choices. It's purely going to depend on the cardinality of the sample set. Okay, well, a more sophisticated thing to do is actually take 1 to A, comma 2B. So you have two 2's, but you're distinguishing them by the sides they're on. And then that leads to a probability of 2 being equal to the probability of 2A plus the probability of 2B, which is equal to 2/3, which I also think is the right answer, by the way, 2/3. Okay, but now suppose I alter the question. That's fine. You can do this if you formalize sample spaces as sets. You can perfectly well do this. Suppose I flip the question a little bit now and I say, how do you formalize the sample space for a three-sided die, two of whose sides are indistinguishable? So assume that these things are actually indistinguishable. So I claim that you cannot do this with a sample space that's a set. At pain of contradiction. And the argument goes roughly as follows. So I'm continuing now from this. So the question, this is the key question, so it's annotated as key question on the handout too. What is omega for a three-sided die with two of its sides being indistinguishable? Indistinguishable. Okay. First option. Omega is 1, 2a, 2b. So it's a set of three things. But then 2a is not equal to 2b. Contradiction. They're distinguishable. The two sides are distinguishable. The other option is omega is 1, 2. But then omega is not a sample space for a three-sided die, because there's only two things here. For 3 being the operative word, sided die. Contradiction. A three-sided die with two of its sides indistinguishable is not formalizable in the classical picture of probability. It's the simplest possible case, in my mind, in which this can happen. Of course, the principle is much more general. Yes?
Sorry, can you just clarify, how are you using the word indistinguishable?
Well, vaguely for the time being.
Okay.
Isomorphic.
My question is more like, are you using it in the metaphysical sense or epistemological sense?
In a literary sense.
Like another way,
I don't know.
From a literary sense, you could ask, who's the subject of the
There is no numerical property between two of the sides. Let's assume that we know that the sides are, there's numbers on each of the sides of the three-sided die. So, and I'm giving a precise answer. There's no numerical property that could distinguish between what is on side A and what is on side B. Okay.
Even though they're like composed of different atoms.
Oh yeah. No, we're not in the physical world at all. It's all about formalization. Bear in mind, it's about formalizing.
Two sides, two things cannot be equal because they're the same.
Well, we'll see about that.
Not equal, indistinguishable.
They're not. Yeah, and they're indistinguishable.
The conclusion of the first argument was not equal. I took the equals there to be equal.
Okay. Yeah, you're right. Okay, let me know. But distinguishable. 2a is distinguishable from 2b.
What distinguishes
No, distinguishable is a relation, defines a relation.
But if you have a verb, that equal is a verb, and equal is just kind of two things you compare. But distinguish is whom is it indistinguishable? Whom is it indistinguishable?
For whom is it indistinguishable?
Who cannot distinguish?
Okay, so
Somebody,
I have a three-sided die.
yeah.
Okay? You don't know it's a three-sided die. I roll it. And every time you either observe one or you observe two. So for you, what I'm doing will be the device that I'm using that shows either one or two will be indistinguishable from, well, you observe the frequency, say, so after a while you begin to realize that 2 out of 3 times you get a 2. But for you, it'll be indistinguishable whether this is an unfair coin with 2 sides, one of which is 2, or a 3-sided die, which is fair. And in fact, since you actually don't know the shape of a 3-sided die, I'm assuming.
I can imagine it like a,
Exactly, even better, which is why this is
But I
is
can't
tailor-made.
imagine I can imagine a three-sided die, and there's no way you could write the twos on there that I couldn't have it up on, because of the spatial, and anyway, I should stop. I mean, I guess, you don't want to answer the question the way I put it, so it's.
No, but if you have the physical thing, yeah, but probabilistically, formally, is there a distinction between a unfair coin and a fair 3-sided die? An unfair in a 2/3 way for you?
I was actually thinking of the object, that I could make a three-sided die, and I had it in my mind, so it looks different.
Okay, but formally, okay, but ignore the physical, formally.
But go ahead, okay, I'll try to.
It means, can you in your class come up with any example about a 2-sided coin that has 1 and 2 on each of the sides, but the 2 occurs with probability 2/3, that you couldn't make with a fair 3-sided die, which has 2 2s on 2 of its sides?
Well, I guess I think that I was just asking Snow's question in my own way, I think, which is, I think of probability as being objective. So even if I could distinguish something.
Okay. Well, 3 perplexions. These are not supposed to be definitive objections or problems. They're supposed to be perplexions. So 3 perplexions. 3-sided coin, Sleeping Beauty, and what is the probability of the Klein group? Okay? 3-sided coin, sorry, 3-sided die. 3-sided coin. That's an interesting concept. Okay. None of these, as I said, my claim is none of these are well dealt with by the classical theory. So now I'm going to define a new way of formalizing sample spaces that at least gives a definite value to all these things, that at least has a way of deducing a value that is mathematically inevitable. Okay. So what do we want? Well, as the question arose, right, that we want what does indistinguishability mean? Okay. So this is section 2 now, definitions on the handout. So what we want is an object omega that has a notion of indistinguishability. Between its elements. Okay. So we want to be able to write things like this. One, we want to be able to say things like this. Omega is 1, say, 2a indistinguishable from 2b. So I'm using this notation for isomorphism because formally this is what they're going to be. We want to be able to write things like this. So we're going to need, so from our desire to be able to write things like this formally, we're definitely going to need this omega, this object that we seek, is going to be something that has points. So it has objects of some kind. But it's not like a set where two of these things are either equal or unequal. It will also include a notion of similarity or isomorphism or something like this. So the simplest example of this kind of thing is, as usual, a set with something. So, for example, take a set X and let this be an equivalence relation on the set X. So this can be thought of as a function, as a subset of X times X. It's a symmetric, transitive, reflexive relation on the set X. Okay, now, whenever I have an equivalence relation, I have a notion of an equivalence class. So this thing, a set with an equivalence relation, will look like something like this. You have elements, say x1, x2, some of which may be equivalent, x4, x5, and so on. The fact that it's reflexive, the fact that it's an equivalence relation, means that x2 will always be equivalent to itself. The fact that it's symmetric means that if this is equivalent to this, this will also be equivalent to this. So in fact, a better way to write this would be there's an arrow from there to there, and there's an arrow from here to here. And the fact that it's transitive, if I again rewrite this with an arrow, means that whenever there's an arrow from there to there and from there to there, there's also an arrow going this way. The same down here. Oh, yes. Okay. That is definitely the kind of structure that we seek. What this doesn't have, though, is a notion of having multiple arrows between two of its objects. So now I'm going to give the formal definition of what I called structure in the title of the talk, and what I've been referring to as a structure. And what it does is basically generalizes the situation so that in addition to having an equivalence relation, you can also have multiple ways in which things can be seen to be equivalent, which is why it deserves the name of isomorphism. Okay, so now I'm going to give the formal definition, which is on the handout. It's the, well, no, it's not the formal definition, the only formal definition. Whether or not you follow the definition doesn't really matter because we're going to rely on specific examples, but I always feel it's better to give a fully precise definition of a notion that's going to be heavily used. Okay, so this is the fabled and legendary notion of a groupoid. A groupoid. So, a groupoid consists of a groupoid X, say. Well, let's write omega. What the hell? Consists of 6 pieces of data. 7, actually. A set written ob omega of its objects. 2. For every object of omega, a set omega, comma omega prime This is just notation, right? So you can think of this as just being indexed by omega and omega prime of isomorphisms. This is just a name, isomorphisms. If you have an intuition about what an isomorphism is, fine. But at this point, it's just a name. Okay, this is the stuff out of which it is made of, the groupoid. And there's two pieces of structure, and they satisfy three properties. So this is structure. Okay. For all objects of the groupoid, a distinguished isomorphism, 1 omega in omega, 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 there's going to be a lot of omegas, 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 called the identity. What is the identity? Well, it's the trivial isomorphism. If you think of these as objects of some kind, it's the isomorphism that does nothing. Okay. This is the complicated one now. For all omega, comma, omega, comma, omega, prime, comma, omega, double prime, objects of omega, and for all isomorphisms P in omega, omega, Q, omega, omega prime, omega double prime, an isomorphism written Q dot P in omega, omega, comma, omega double prime, called the composite. So what is this doing? What does this mean? Go back to this example. This is omega here. This is omega prime in the way it is in the definition, omega double prime. So it says whenever you have some P from omega to omega prime and some Q from omega prime to omega double prime, then you have something which we're calling Q times P from here to here. If you think of these arrows as functions, it's the composite function. Okay, such that three things are satisfied, three conditions are satisfied. One is a left and right unit, which means that the identity isomorphism followed by some other isomorphism is the same as that isomorphism is the same as that isomorphism and followed by the identity. Composition is associative. Which I'll draw graphically. This means that if you have three successive isomorphisms, okay? There's two ways you can compose them according to this definition. One is you first join these. Let me use another color. First you join these and then compose with this to get this. Or first you join these and then compose with this to get this. And the associativity axiom says that these two things are the same. Okay? And inverses. Inverses means for all isomorphisms P from omega to omega prime, there exists something called P minus 1 going in the other way. Omega prime, comma, omega, such that when composed either way, they give the identity. That's it. So what is this thing? This is the completely precise definition. I haven't skipped anything. It's maybe a bit long, but at least it gives you the, nothing has been shortened. It is every single piece of data that is needed is there. Okay, what's the best way to understand it? Generalized abstract nonsense, examples. So let's do some examples.
Just a general question. You haven't really left set theory.
Oh yeah, of course not, no. I'm using set. Definitely. Everything I'm doing today is in set theory. That's why I said there's not going to be any type theory. Sample space is a set, yeah. In the classical theory.
Go ahead.
Okay. Examples, just to understand what this kind of thing is. Okay. Take a set with an equivalence relation. Okay? I can turn this into a groupoid, into something of this form. How? So, and let's call this Gx. Okay? So Gx is a groupoid. Actually, it should be indexed by the equivalence relation as well. So the objects of Gx are the elements of X. Set, a set. The objects are a set, definitely. And whenever you have 2 points, whenever you have 2 objects, 2 elements of X, the set of isomorphisms between X and Y is equal to the empty set if X is not related to Y by the equivalence relation, or just some formal symbol, which we can write this way, if X is related to Y by the equivalence relation. So what this is doing is it's basically formalizing what I wrote down before. It's taking a set with an equivalence relation and it's visualizing it as a groupoid by writing out all its elements. And whenever these elements are related by this equivalence relation, it adds an arrow going both ways. Finite sets. That's another groupoid. What are the isomorphisms? Okay, well, let's define it. The objects of finite set, fin set, usually written, are the finite sets. Okay? Now, if S, T are finite sets, this is the other piece of structure I need to give, right? What is fin set S, T? Well, I define it to be bijections from S to T. The set of bijections, multiple arrows from S to T. So if S and T don't have the same cardinality, this thing will be empty. If they do have the same cardinality, it will be the number of bijections between them. So in the special case where you take subsets of the natural numbers, for example, then you have only one object. A special case of this is exactly the same definition, but we take, instead of taking, okay, let me write it here. Let's say numbers, num. You take the objects to be subsets of n of the natural numbers, which we can write as like this. Okay? And in this case, the isomorphisms between any two such things will be the permutations of the set of n natural numbers, of which there are n factorial. Okay. Well, these, no.
No. The third number 3. I mean, you could. This is certain types of subsets of the natural numbers. Of
Right,
course,
ordered,
n-minus-
yeah, right. Yeah. Ordered ones, yes. Or you can take, or you can think of it this way, right? You pick a canonical representative. For each natural number, you pick one set that has n elements. For each natural number n, you pick one thing. That can be just as well will be the objects of this. Okay, all right.
So just a historical question, this concept of a groupoid is something that was invented after category theory.
Well, actually, it predates the definition of a category, believe it or not. Now, usually, usually a groupoid is defined as a category with an extra property, namely a category in which every arrow is an isomorphism. But actually, the definition of a groupoid, which is really a group with multiple carrier sets, that's really what it is, was actually defined before MacLean and Eilenberg's work. It was defined when by a guy called Brown or something like that. It was a paper in German.
Like 20th century.
I think it was late 19th century. And he was studying what used to be called invariant theory in the day of Hilbert. So it was basically the study of, I think, what were they? Solutions to polynomials, more or less. Something very concrete, mathematical. So it was a generalized way of classifying the roots of certain generalized polynomials, just as groups were originally defined as acting on the roots of polynomials. Okay, all right. So this is the definition. This is the definition of a groupoid. And now let's take this idea seriously. Now I want to say my sample space is, okay, let me actually give you the fourth example just to appease you. The fourth example, every set is a groupoid. So sets can be recovered as degenerate cases of groupoids. Namely, take any point in the set, add a little loop to it, the identity gives you a groupoid. So you're not losing the sets by doing this. Okay, we're generalizing. So now let's, yes, in that case. So basically,
What was your comment? You said a group is a groupoid is a group with what?
with multiple elements.
With multiple elements.
Yeah, because look, with multiple carriers, you should say. What are the axioms for a group? You have an operation that's associative and has an inverse, right? That's basically exactly what I defined here. The only difference is that there's multiple dots with their own group structure. Okay. Okay, so idea. A sample structure, what gives the title to this talk, is a groupoid, omega. Okay? Question, immediate. What does it mean to sample uniformly from omega? Surely if we're going to do some kind of probability in this setting, we need to have such a notion. Uniformly from omega. So one option is, now I'm using notation that is not precisely defined, just trying to mimic the classical thing you do. This is a random variable uniformly distributed over omega. So you can say the probability of this thing, since this is a groupoid, and as Glenn pointed out, is a set, well, why don't we just do the same thing we do back in the old classical theory? It's just going to be 1 over, oh, and I'm assuming finite, okay? Okay, sorry. Finite groupoid, where finite means that the cardinality of its set of objects is not infinite, okay? So, why don't we take this? 1 over the size of the set of objects. No, but this is a terrible idea. Why? Well, because you might have a groupoid that has millions of objects. It might have 1 million objects. Let's say it has 1 million objects. But all of them can be isomorphic one to the other. So up to isomorphism, there's only one object. But this would give the probability of something being sampled from it to be 1 in 1 million. Okay, so we do something more subtle. And this is the magic formula. When our sample spaces are groupoids, we define the likelihood that something sampled uniformly from omega is isomorphic to some little omega in there as the following thing: 1 over the cardinality. I'm going to explain what these things are. I'm going to write it first. Wait, this is important enough that I need to erase the nonsense option. Times the cardinality, something that I'm going to call the size, the structural size of the groupoid. Okay. What is this? Well, this is just the number of isomorphisms from omega to itself. That's all it is. You can call them automorphisms if you would like. Nothing more. So, in this case, for this groupoid, the number of isomorphisms from X to itself is always going to be equal to 1. For this case, the number of isomorphisms from a set S to itself will always be equal to the permutations of that set. So number of isos from omega to itself. Now what is this? Now this is where the good stuff happens, right? Okay, obviously it's not the cardinality of the object set of omega. I said we're discarding this. So what this is going to be, what we want it to be, is something that measures the elements of a groupoid, the objects of a groupoid, up to isomorphism. And I'm just going to write out the formula. So let me introduce some notation. I'm going to give you the mental picture that I have in mind. After. Okay? So fix an omega. That's a groupoid. Write omega for the equivalence class. So omega, little omega is an outcome in here. Write this for the equivalence class of this thing up to isomorphism. So it's the set of all objects of omega such that omega is isomorphic to omega prime. Okay? And write pi 0 of omega. This is notation that comes from topology. It's the number of isomorphism class, the set of isomorphism classes. So it's the set of all isomorphism classes for all things, for all objects of omega. Okay? So now, the structural size of this thing is going to be the number of isomorphism classes it has weighted by the number of automorphisms in there somehow. Okay. So this is the key definition. The structural size of omega, written omega bar like there, is the sum over all equivalence classes in pi 0 omega of 1 over the size of the automorphisms of omega. So what this measures is, for every object in the group, for every isomorphism class, it adds something in there. Whenever two objects in a group are isomorphic, they will always have equal cardinalities of these sets will be equal, which is why this is well defined. The choice of the representative doesn't matter. We're counting the number of ways in which an object can be seen to be isomorphic to itself against it. So the more ways it has, the more automorphisms it has, the smaller the number associated, the smaller its weight is going to be. So my picture of it is, the more automorphism something has, the more ghostly it becomes, because there's more and more ways in which you can isomorphically permute everything that's in there, so it becomes a blur. So as you move up the numbers, the greater the numbers, the greater the permutation, the greater the number of permutations of them, so they become more and more blurry, more and more ghostly. So the probability that they're there becomes less and less. That's a bit of philosophy. Okay. All right. So this is the formula. Okay. So the precise definition now, let me write it out in full. It's worth it. Is omega times, let me write it separately, 1 over the sum over all equivalence classes omega of the size of the, oh, sorry. Oh, yes, it's 1 over. I wrote it. 1 over omega. Okay, there's a few components, but it's very simple. It's extremely simple to calculate. There's no deep mathematics going on there. So this is what it means for something to be sampled uniformly up to isomorphism. This is the formula.
So,
Yes. Yes. You can prove it. Yeah. And it's well defined. There's a couple of lemmas that you need to prove. Like a priori, you should be wondering whether this is well defined, because obviously I'm selecting a representative and then plugging the specific element in here. But it's fine. It works out. Yeah.
Infinite groupoids are the number of isomorphisms from each element in the object set to itself. I don't see how it follows that those objects are finite. From the axioms you gave us.
Yes, I'm assuming that. I'm assuming all the little omegas are also finite. Yeah. Good point. You don't have to be, but you need to modify the definition slightly. None of this is an obstacle to being generalized, but for the time being, to illustrate. Yeah. So all these things for all little omegas is finite. So everything is finite. Okay. Why? Glenn is asking why.
no,
Well,
I'm trying to get.
no, I'm being rhetorical. I'm being rhetorical.
Trying to get that if you want.
Why is this? It solves all three of these problems. So let me conclude by telling you why this formula is kind of a magic formula. So I have 3 sections. One is titled problems, second is titled definitions, the third is titled solutions. So
Well, before you do that, is there something, is this adding up to 1?
yes.
Is that easy to see?
No, it's slightly non-trivial, but it's kind of immediate. Yeah, it does.
It is immediate.
Just you sum over all the little omegas on the outside of that thing.
yeah, the weighing is, it's exactly analogous to when you say that the size of a set under an equivalence class is the sum of 1 over, the sum over all the equivalence classes of 1 over the size of the equivalence class.
Ignore the thing on the right side. Ignore the 1 over sum, and just add, which doesn't depend on omega, and add up these 1 over omega, omega, omegas. You add them up, then that equals that.
Yeah. So this does behave like a probability indeed, yes. But the way to read this is the probability that something sampled uniformly out of the groupoid omega is isomorphic to omega. That's why I've written it this way. So it's a generalization of the classical theory. Okay, now solutions. Solutions. No one should write the formula like this if there isn't something that it solves. So I think it solves all 3 problems. So let me conclude by saying how. Actually, I'll start from this. I'll take them in the opposite order, because the first problem is the coolest one, actually. Okay, so the 3-sided die. How should you formalize it? Well, I claim you should formalize it like this, as a groupoid that has 2 objects and 1 non-trivial isomorphism for one of them, namely the number 2, what I was calling number 2 before. Why do I think this is reasonable? Because as long as you say that you have a 3-sided die with 2 of its sides being indistinguishable, that means you definitely do have 3 sides, but 2 of them, you can non-trivially modify the die, flip it, or change its direction such that you get the same thing. So I think this is adequately captured by this groupoid. Okay, let's do a bit of math now. The probability that the roll is equal to 2, I'm just going to apply this formula, right? So in this case, with this omega, pi 0 of omega is consists of 1 and 2. Okay, just 2 equivalence classes. So this is equal to 1 over the automorphisms of 2 times 1 over one over 1 plus 1 over 2. If you do it. Now what is this? No, wait, no, 3, 2, 3. This is going to be, no, this is not going to be 2.
You have the identity automorphism as well. You have the flip.
This is definitely going to be 2, yeah, but it's not what I wanted. I might have miscalculated. Yeah, I miscalculated. Anyway, this goes back to when I wrote this down. I was telling myself that in some cases it's more intuitive to actually write 1 minus this as the probability.
To leave out the identity.
To leave out the identity, yeah.
No, not to leave out the identity.
No. 1 minus the whole thing, that it's the opposite of the probability.
Oh.
Yeah, there is a miscalculation there. Anyway, whatever, it's a third. We need to follow the formalism. So I suppose that...
Okay, so you didn't solve that one.
Well, I mean, but there's nothing to solve, really. I mean, it's you're taking a notion of a probability and you're following the consequences. Yeah. Okay, it's a third. So why? Because it's 2 times 3 over 2. Okay, so it's a third. Anyway, half solved, half solved. This one is half solved. Okay. Now the Sleeping Beauty problem. I'm more inclined to trust the mathematics, whatever it says. So maybe the three-sided die, the probability is actually a third.
But it's a paradox.
Okay. What?
I would think that here, the question you want to answer is not x equals to 2, but x is isomorphic to 2. And if that's the probability you want to calculate, then on top of that formula, you probably want to sum over all the probabilities of omega prime that is in the equivalence class.
I'm not sure. Would that sum to 1?
Well, I think this is a typo, actually.
Which,
I think
which one?
I think
Let me
what
see.
you want to answer is probably that x is isomorphic to 2 in section 3.1. You wrote probably x equals.
Yeah, that should say isomorphic. Yeah, sorry. Okay, Sleeping Beauty problem, Sleeping Beauty problem. Okay, let's see if this one gets solved. Okay, so Sleeping Beauty problem, I say the sample space should now be a groupoid where you have Monday heads, Tuesday tails, Monday tails, Monday, Tuesday tails, and one isomorphism between, and an isomorphism between them. Okay? Why? What's the justification for this? Well, it's because the way the experiment is being set up, Sleeping Beauty is being told that they're indistinguishable, that she's not going to remember. So the pill in this rhetorical setup, she's given a pill. The pill, I think, formally is best captured as an isomorphism, as something that witnesses an isomorphism between these two events for Sleeping Beauty. Okay, so now let's calculate the probability. So let's do it this way differently. So the credence, Sleeping Beauty's credence, I'm going to write it as SBC, that the coin landed tails, I say, so this is by definition, this is not a proper equation, I say should be the probability that, so C is a uniformly sampled over this groupoid, is isomorphic to Monday tails, say. Tuesday tails won't make a difference, hopefully. And what is this equal to following the formula? Well, it's equal to 1 over, let's be very careful now. So 1 over the automorphisms of MT, the size of the automorphisms of MT, times 1 over, now it's going to be, there's 2 components, but there's only 1 automorphism, so this is going to be 1 plus 1. There's no non-trivial arrow here. So this is actually equal to 1. Only the identity is in here. So that gives a half. Which for me solves it, because I think that's what the answer should be. Okay. That makes me think, that is probably an argument for it being 1 minus. This is what, because this will still come out the same, whereas the previous one will also be solved.
What is 1 minus?
There's 2 ways to go with the definition, right? I'm doing mathematics, I'm formalizing here. I initially considered, and this is why the example was a bit muddled up, I initially considered defining this probability of sampling up to isomorphism as 1 minus this. So I wanted this to be the definition, which would have given the right answer in the first case. Well, you know, it's all under.
This is a huge choice.
I'm syntactic, you know that. It's a theory. But in any case, this choice would have gotten the other case, right? Okay, the fourth one. Now this is the most interesting one because I don't think it's something that people have intuitions about. Well, Isaac said a half. But still, let's do it. So let's do the first one now, the Klein group. Okay. So the first one. So here, I agree. Let's take the sample space to be, so let me remind you, you're given a set with 4 elements with a group structure. You're asked, what is the probability that the group structure you're given is the Klein group? So let's take the sample space to consist of C4 and V. So the cyclic group on 4 elements and V. But as a groupoid. What does it mean as a groupoid? There's definitely no isomorphism between those two things because they're not isomorphic as groups. However, there's many non-trivial automorphisms. There's a non-trivial isomorphism of C4 and a trivial one, the identity. And there's 6 automorphisms, including the trivial one of the Klein group. So this is actually something that looks like this. Okay. So now the probability that a randomly sampled group is equal to the Klein group from the sample space is going to be equal to cut. Actually, maybe I should do the calculation because I messed up the other one. So this is going to be 1 over omega v comma v times 1 over a half plus a sixth. And this is equal to 6 because there's 6 here. There's 6 arrows. So this is a sixth times 1 over times, let's be very careful, times 4/6 is equal to a fourth. Or 3/4, depending on what choice you make here. In any case, not a half. Why? I don't know. And I don't care. The most interesting situation is when you have a reasonable mathematical definition, fully rigorous, reasonable mathematical definition, arguably gets some of the cases right, which gives numerical answers to things you had no intuition about.
But I feel like I had a very good intuition about that.
It's the wrong one, I'm afraid.
So the intuition is this.
Okay, but this is the punchline. Okay, right. Let me get, literally I have one more sentence. Yes, so in situations where you have these numerical answers obtained from definitions that make sense in other cases, I think that's the most interesting bit because then you can ask why. Okay, so there's some philosophy, I suppose, to be done at this point. But the main thing was, I feel, in order to solve these cases adequately, or at least formally approach them, you need to generalize the theory of sample space, of the way in which probability is being formalized in terms of sample sets to sample structures of some kinds, like groupoids. Okay, that's it.